Okay, so I'm going to go over question 3 and 4 on the determining formulas worksheet. So 1 and 3 actually mirrors of each other, and 2 and 4 are mirrors of each other. I'll post the answer key fully, but just if I go over 3, it's like I'm going over 1. Okay, same with 4 and 2. All right. So, 3 says cyclopropane, a gas used with oxygen as a general anesthetic, is composed of 85.7% carbon and 14.3% hydrogen by mass, which means you can convert those percentages to grams directly. You can say you have 85.7 grams of carbon and that you have 14.3 grams of hydrogen. Okay, so the first thing we would do here is we would convert these into um, moles. If you read the question carefully, you'll notice that this is basically just an empirical formula question in gas language. Okay, so quickly convert your carbon. I got 7.14 moles of carbon, and let's see, hydrogen. This is just hydrogen by itself. This is not your diatomic hydrogen, okay, because this is percent by mass. So I got 14.3 moles of hydrogen. So obviously I have more moles of hydrogen than I have of carbon. Just like empirical formula problems, you must divide by the smaller mole number. I'm going to divide by 7.14. Both of those values should be divided by 7.14. That gives us 1 mole of carbon. I actually like to write it differently. I like to write it in the way that you would write the formula. So I have carbon and hydrogen, 7.14, and I have 14.3. Divide both by 7.14. This gives you 1, this gives you 2. So then your formula is CH2. This is the empirical formula, kids. Okay, we're looking for the molecular formula of whatever this compound is, cyclopropane. All right, now we can use the equation from the PowerPoint that helps us calculate molar mass given the mass, the gas constant, the temperature, the pressure, and the volume, all of which we have. If you forgot where this came from, you remember that moles, if you just look at the regular version of the gas equation, it's just Pivnert, but the N is mass over molar mass, right? Mass divided by molar mass gives you moles. So you can replace the N with mass divided by molar mass. And if molar mass is capital M, you can solve for molar mass here. Okay? So let's plug these values in and solve. We are looking for the molar mass. Our mass is 1.56 grams. Gas constant is 0.08206 liter atmosphere mole Kelvin. Temperature is 323 Kelvin because it's 50 degrees plus 273. The pressure is 0.984 atmospheres and the volume is 1 liter. Okay, that makes things simple. So this is just to find the molar mass. So the molar mass is going to be 42.0 grams per mole. You'll notice that all the units cancel out other than, whoops, there I go canceling out moles, other than moles and grams. Okay, ATM cancel out, Kelvin cancel out, liters cancel out, leaving you with grams per mole, which is the units for molar mass. So that's kind of satisfying. Let me just get some more space here. All right. Now that you have the molar mass of the actual molecular compound, what's left to do is to figure out the molar mass of the empirical formula, which is just going to be 12.01 plus 2.02. So this is going to just be 14.02 grams per mole, okay? And you can just divide, we'll go with 366, Celsius is 14.0 grams per mole. Let's find the molecular formula. That is going to be MF mass divided by EF mass to get N. So that's going to be 42 grams per mole divided by 14 grams per mole, which will be 3. So CH2 times 3 gives me C3H6. That is the molecular formula of this compound. Okay, so it's basically an empirical formula problem, but it just has the gas equation in it, the ideal gas equation in it. Every time you get variations, you can use like the different equations that you're given to figure out how do I apply the equation to this particular problem. Okay. Now question 4 is also a empirical formula kind of problem, but it just has the principles of finding empirical formula built into it, like mole ratios. Okay. Now you have the combustion of 135 milliliters of a gaseous compound happening. It only contains carbon and hydrogen. It requires 675 milliliters of O2, 405 of CO2, 0.434 grams of H2O. All gas measurements are made at STP. That's super important that it's made at STP because that basically makes this problem super easy to do. So at STP, 1 mole of gas occupies a molar volume of 22.4 liters. That can be used as a conversion factor to figure out moles given volume, okay? So we have 135 milliliters, which is just going to be 0.135 liters of some gas X, right? That contains C and H. Actually, I'll just do this. CXHX, some value of CXHX. You can convert this into moles. 1 mole of this 22.4 liters. I'll just remove that. That's going to be annoying. Okay, so this is going to be 0.00603 moles of CXHX. Then you have 0.675 liters of O2. Again, you can use the molar volume, 1 mole over 22.4 liters. And that gives me 0.0301 moles of O2. Then the next one is, what's the gas? CO2. I have 0.405 liters of CO2. Convert to moles. Gives me 0. Sorry for all the movement of the screen. It is what it is. 0.0181 moles of CO2. And I have 0.434 grams of water. You just use the molar mass of water to get moles of water, okay? 18.02 grams. That gives me 0.0241 moles of water. Actually, I'm just going to make some space for myself here. It's going to be CO2. It's going to be O2. And this will be moles of CXHX. So if you look, the smallest number is the moles of the CXHX. If you divide it by itself, you're just going to get 1 here. And then if you divide, so this is where the empirical formula principles come into play. You are just trying to find the ratio of each component to the one that you have the least of. So you just divide everything by the smallest mole number to get those ratios. So if you divide this by 0.00603, you should get 5 moles of O2. If you divide this one by 0.00603, you should get 3 moles CO2. So you have 1, 5, 3, and then if you divide this one by 0.00603, you should get 4 moles of H2. H2O. So let's write this out like an equation, which is what this is asking us to do. So I have 1 mole of CXHX plus 5 moles of O2 reacting to produce 3 moles of CO2 plus 4 moles of H2O. Since there's only 1 mole, we just have to count the number of carbons and hydrogens on the product side. I have 3 carbons and 4 times 2, 8 hydrogens. That means my compound is going to be C3H8. It's just propane. That's the compound in number 4. Okay, so that's how you solve that kind of problem. You use your molar volume, you get your moles, you divide by the smallest mole number, and then you basically just count how many carbons and hydrogens are there. And if this stoichiometric coefficient right here was greater than 1, you just have to figure out based on it how many carbons and hydrogens again. Okay, very simple to do.